We're going to finish section 1.2. We had left off talking about triangular numbers last time. You guys remember that? We had these images that created a shape. And we have another set of figure numbers that we're going to work on, and they're square numbers. All right, so we have these images where I've got 1 dot, and then I've got 4 dots, 9 dots, 16 dots. And these are called square numbers, and I know my pictures don't look very square. Yours were going to look so much better, I'm quite sure. I told you I wasn't an artist at one point, I think. So definitely not an artist. But can you see what's happening to this shape as the shape gets bigger? What are we doing to the shape? Yeah, you're adding a row and a column, kind of, right? So you're making the figure bigger by adding a row and a column. So in other words, if I were to take this image, these dots right here are what got added or included on the new figure that weren't on the figure before, right? The row and the column. So if I were to create the next figure, what would it look like?
5 dots on the bottom, 5 across.
Yeah, so it'd be 5 dots wide and 5 dots tall, right? I think that's worse than the one before. Pretend like it makes sense and it should look square, because if it's 5 wide and 5 tall, it should look like square, and I'm pretty sure those don't look like squares at all. But imagine that they do, all right? If we write out the number of dots in each one of these images, you can see that we actually have this list of numbers here below. 1, 4, 9, 16. What would the next one be? 25. Do you know what the next one would be without drawing it and counting? 36 and 49. And this actually has a form, as a general form of what are we doing? These are squared. These are actually whatever term I'm on squared. So the first one has 1 dot because that's 1 squared. The second one has 4 dots because that's 2 squared, and so forth. I'd like to show you something I showed you last time. Over here we talked about first differences and second differences. Do you remember that? I just want to show you that that works again on this one as well, because you're going to be doing some where you don't have images to go with. And so if you take a look at this one, to get from 1 to 4, what do? Add 3. How about from 4 to 9? You add 5. How about from 9 to 16? You add 7. How about from 16 to 25? Add 9. 25 to 36? You add 11. And then 36 to 49? You add 13. Now, this is definitely not arithmetic, because I didn't get the same number on these here. But you do see a pattern amongst the numbers, right? Mm-hmm. So if you didn't recognize, hey, these are all squares, and maybe it's because they weren't. Maybe instead of it saying 1, 4, 9, 16, it started out saying something like 2, 5, 10, 17. Well, I don't know about you, but if I saw 2, 5, 10, 17, my mind would not think, hey, squares of numbers. It would probably do something like this. I'd try to figure out what's the difference between the things going on. So I'd get a list much like this one, and I can see a pattern in this list even if I didn't notice the squaring pattern before. And if you didn't see the pattern in this list, you could do it again. 3 to 5 is 2. 5 to 7 is 2. 7 to 9?
2.
So they're all plus 2s, right? So this is actually a sequence that I can get to using second differences, because the second differences all match. Okay? And again, if I wanted to do the next one, I could actually take plus 2 here. 13 plus 2 would be 15. And I could do 49 plus the 15 to get the next term, even if I didn't recognize that it should have been 15 before. So what would I get? 64. And we could keep going. Yes?
So it's not arithmetic, though?
No, it's not arithmetic, because for it to be arithmetic, the first differences would have had to match. All be plus 2.
So what would you call that?
It doesn't have a name.
Okay.
It doesn't have a name, but the second differences are where we actually get the sequencing matching, all the 2's matching.
So would you just say neither?
Yeah, this would be neither. Like if you were asked, is it arithmetic or geometric, this one would be neither. Good question. Okay. Any questions on that? Okay, I want to show you an interesting thing. This actually happened a few years back. In 2011, things changed at OBU, and we created the 6 colleges that you see here now. So we actually have a College of Science and Mathematics. I say mathematics and science, but apparently officially it's science and math. And so when the Hurley College was created, the first meeting of the year, Our dean actually put on the board, I think it was her, but it was someone else, it wasn't me, put on the board the number 3.1415. And they were asking us to find what are the next terms in the sequence. It's sort of generic, it doesn't say how many terms, but what are the next terms in the sequence? So without talking to anyone, I want you to write down what you think would happen next if this question were posed to you. What comes next in this sequence of numbers?
How many do
Just write a few. I'm not going to be specific. All right, so what did you write? What'd you guys write next? What comes next? Let's say the next three terms. And then so you're 7. Okay, somebody write anything different? What'd you write?
3.14159265.
All right, so what I had you do is I had you actually do one of those types of reasoning we encountered last time. Let me go back to this page where we talked about them. I had you create something based on inductive reasoning. I gave you a little piece and I said, what do you think comes next, right? So those of you who did the first one, 1617, you were looking at the numbers as though the 1, the 5, the 1, the 1, 4, 1, 5, and you said, I see a pattern in 1, 4, 1, 5. Agreed? Okay. So Katie, right? Katie, you did something different. What did you recognize?
Pi.
It looks like pi. 3.1415 looks like pi. And so what I want you to recognize in me asking you this question is that when you make inductive statements, you are making generalizations based on your previous exposure or your experiences. When I saw this number at this meeting, I did what Katie did. But not everybody in our meeting actually did that. Some of them did what you guys did. Now, most of them did what Katie did. Do you know why?
Because you guys
We're math and science people.
So you know pi.
And so pi is one of those numbers that we know something about and we use frequently. But most of you didn't do what Katie did you? Because pi is not a number that you use in what you do all that often. Okay, so inductive reasoning may or may not actually get us to the right solution. Interesting, right?
The pi that we mostly use is just 3.14.
The one that you use the most time is 3.14. That's true. Yeah. All right, so this homework set, we're finished now with 1.2. And we'll do group work here in a little bit.